Hey guys, this is Noah Housley with another dynamics sample problem. I'm taking from sample problem 11.8. I only do these sample problems because I just want to make sure I'm not telling you guys wrong things, and so they have the right answers given already on there, so I'm just making sure. Okay, so we have this pulley system. Okay, so at first I could look at this pulley system and I kind of go like, shoot, I don't know what to do with that. But just like girls, when you don't know what to do with them, you date them. So set the datum. All right, so the datum means that it has to be at somewhere that doesn't move. Okay, and on this system, the only parts that don't move are the top two pulleys because it's tied to the wall. All of this stuff can move. Okay, so I'm going to draw this dotted line. I don't know if that's easy to see or not. All the way across, right there, datum. Okay. Next step that Professor Magleby described is to describe the cable. Okay, now what that means is see how long it is. In this problem, we have two cables. There is one connected to this A and then to the bottom of B, and then this one that goes around here to C. Okay, so let's start with cable 1. I'm going to call this cable 1 over here. Cable 1. Okay, how long is it? So we judge it from the datum. So from the datum, it goes to A. So I have some distance y to A. So I'm going to say L equals YA. Okay, is that it? Well, I also have this piece that goes to here, and be careful not to be confused. This is not a constant. This can change. You know, imagine if B was more up, then this would change, and A could stay the same, and these two could be the same length or something like that. So this is not a constant. Usually, you only have constant when you have it between two fixed points that don't move. So like up here and here, this in between, that's a constant. Or around a pulley, that's a constant. Or in between a wall and a fixed pulley, that would be a constant kind of thing. Okay, so it's between two fixed points. So since we don't, though, from here, how long is this? And my drawing is bad. The one in the book is more clearly. But this one is, let's see, so if this is length B, and this is length A, and this is in between A and B, then it's going to be plus a YA minus the YB. And that'll be that distance there. Okay, that's my first cable. So combine this. L equals 2YA minus YB. Okay, I'm going to stop there. Okay, so I can do cable 2 now. Cable 2, let's just do it fast. This distance is to B, this distance is to B, and this distance is to C. So we got 2YB plus YC. That equals L. I'm going to put L2 and L1 over there. I don't have to combine that. That's already combined. Okay, so what's our next step? We've dated the girls, set a datum. We've described the girls, and now we're going to throw away the girls. Well, we have just our one constant up there. So, okay, throw away the constants, you know, the girls that are just constantly the same. By the way, I'm married, so I can make dating jokes. Okay, so now step 4, we're going to take the derivative. Okay, this is super cool, and this is also why we can throw away the constants. So when we take the derivative of a distance, and this is a constant, right? The cable length is not going to change, and so when you take the derivative of that constant, it's going to be 0, and the same thing for over here, 0. Okay, and that's going to equal something. Okay, so then when you take the derivative of a position, and right now, think about this as a function, right? Because depending on the movement of the cables and the blocks, there's a function and that we have no idea how to get, and but why would we care, right? Because we can just derive y and get it. So we have 2, and then derivative of position is a velocity, so we have now VA, and then minus VB. Bada bing, bada boom, the same thing. 2VB plus VC. Excuse the handwriting. Okay, so now we have these two equations. take it a step further. Derive again. Get the acceleration. So we have 0 is equal to 2a of a minus a of b. 0 is equal to 2a of b plus a of c. Okay, very good. Now let me click on the problem. The problem says, so now we've done that. Now we just need to look back at the problem, see what it wants. It says, block C starts from rest and moves down. Okay, that's important to note. Starts from rest and moves down. Note, the datum is up here and it's moving away from the datum, which is in the positive direction. Okay, so C is moving in the positive direction. That's important to know. And to not get tricked up with the datum, just think the global datum that we usually have is the ground. And when you go up from the ground, we usually feel comfortable calling that positive. And so just think of this is the ground. You want to get away from the ground. You want to go up. Or in this case, an upside down up. Not down, it's an upside down up. Okay. So it's going away. So it's going in the positive direction. And a constant acceleration. It's had that C word, constant. That means we can use the kinematic equations. Knowing that after block A has moved 1.5 feet, okay, that's interesting. So interesting info. Block A has moved 1.5 feet. Its velocity is 0.6 feet per second. Okay. Now determine. Now once it's find. Okay. So find the acceleration of A and C. Okay. A, C, and A. Okay. Right there. And then the change in velocity and the change in position of block B after 2.5 seconds. Okay, so change in VB, change in YB. Okay, all right. I'm going to put XB just for the sake of later on. Okay. All right, that's all we got to do. Okay, well, AC and AA, well, we have 2 equations and 3 unknowns. Well, that sucks. But they've given us some information. Block A has moved 1.5 feet at a velocity and is now at a velocity of 0.6 feet per second. We have a kinematic equation that will tell us this. So not using time, we have the current velocity squared is equal to the initial velocity plus 2ax. Now we can find a because we have x, this is 0, and this is 0.6. So 0.6 squared is equal to 2a times 1.5. When you do this, it comes out to 0.12 is equal to, I believe it's 0.12. 0.6 squared divided by 3. Yeah, 0.12. And equals a. And this is a of a. Well, now we have 2 unknowns with 2 equations. Boom, we can solve this baby. All right, so I'm going to plug in. This is 2a of a equals a of b. And here I have 2a of b is equal to negative a of c. Okay. So if this is important to note. Which direction did A move, do you think? Well, if C is moving down, that means it's pulling on that rope, which is pulling that up, which is pulling that up. And so I think A is moving up, or towards the datum, which is a negative. So I think it's important to say that the velocity, or really direction, is negative. It's moving in a negative direction. And so we're going to have a negative 1.2 acceleration. That way when we plug in for B, well, so let's substitute here. So we have 2 A of B equals that. So we have 4 A of A. 4 A of A is equal to a negative A of C. Okay. So that's a negative 0.48 is equal to a, oops, sorry, you can't see. A negative A of C. And so divide by a negative. A of C is equal to 0.48 feet per second squared. And A of A is already negative 0.12 feet per second squared. I did squared per second. It's second per squared. Okay. All right, so that's part A. We've done that. Check that. Okay, now change in velocity and change of position in B. Okay, so once again, just use the kinematic equations. It says change of velocity and the change of position of block after 2.5 seconds. Boom, it's giving us time. Time equals 2.5 seconds. So change in velocity, well, that's easy. If I just have what my velocity is now, and I know it started at 0 because C started at 0, so I got 0 there, plus A times T. Well, I can find my A, and I can find my T. A was just doubled the A's acceleration, which was 0.12, so this is negative 0.12, so this is negative 0.24 times time, and that comes out to be 0.6. So this velocity is 0.6 feet per second. That's the change of velocity B. Almost there. Now the change of position, well, we've got so we want the change in position, x. We know it started at 0 position and at 0 velocity because C started at 0 velocity. And now we just have 1/2 times A of B, which was negative 0.24 that we found, times 2.5 squared. Comes out to be negative 0.75 feet. And there's our answers, okay? All right, hopefully that made sense. Post any questions if you got them.